Hello everyone, and welcome back. In this lecture, we move to another very practical and very important part of chemometrics, data processing. And this is one of those topics that may sound a little dry at first, but in reality, this is where we decide whether our data will behave like civilized scientific information or like gremlins. So today, we will talk about how to deal with suspicious values, how to transform variables when needed, and how to prepare data so that later analyses actually make sense. This part of the course is all about preparing data for serious chemometric work. We already know that collecting data is not enough. We also need to check them, clean them, and sometimes transform them, because raw data are not always ready for analysis straight out of the box. Sometimes they contain strange values, distorted distributions, or relationships that are clearly real, but not nicely linear. And if we ignore all that, the latest statistics may become very elegant and very wrong. During data control, we often encounter outliers. These are objects or samples with at least one feature that differs strongly from the rest of the dataset. And then comes the classic dilemma. Is this a mistake? Or is it a real value that tells us the sample may come from a different general population? That is a very important distinction, because if it is a mistake, we may want to remove it. But if it is real, then it may actually contain valuable information. Statistics can help us here. But there is a catch. The rest of the data should exhibit something close to a normal distribution. So as usual, life in chemometrics is not impossible, just conditionally complicated. Before performing any mistake or outlier test, we should first make a histogram of the feature showing an unusual minimum or maximum value, and importantly, the suspected outlier should be temporarily removed from the dataset before we inspect the remaining distribution. Then we ask a key question. What if the distribution of the remaining data still deviates from normality? In that case, the suspected point should be restored to the dataset, and a transformation should be applied to the variable whenever possible. So the outlier test is not the first move. The first move is stop, plot, think, and only then start removing things. A surprisingly good rule in both statistics and life. For small datasets, there is a quick outlier test called Dixon's test, usually denoted by Q. It is designed for datasets with n less than or equal to 10. Before using it, the values must be ordered in non-decreasing fashion, from the smallest to the largest. And because either the minimum or the maximum may be suspicious, the test has two separate formulas. So Dixon's test is basically a small dataset specialist. Fast, handy, and a little picky about order, which, to be fair, is a very statistical personality trait. Once we calculate the Q value, we compare it with a critical value, called Q critical, which depends on the size of the dataset. If Q is greater than or equal to Q critical, then the outlier is considered real and should be removed from the dataset. This slide also shows the critical Q values for significance level alpha equal to 0.05 for datasets from 3 to 10 observations. And one thing becomes obvious immediately. For very small datasets, Q critical is quite high. So in tiny datasets, Dixon's test is rather conservative. It does not accuse points lightly, it wants evidence. This slide gives a very nice visual intuition for Dixon's test. It shows how the apparent separation of a suspicious point is judged differently depending on whether the dataset has 3, 5, 7, or 9 observations. And the message is simple. The same visual gap does not mean exactly the same thing in datasets of different sizes. So once again, context matters. A lonely extreme point in a tiny dataset is not interpreted the same way as a lonely extreme point in a somewhat larger one. Statistics loves context, and honestly, that is one of the reasons it is both annoying and useful. For slightly larger datasets, meaning more than 10 observations, a better option is student's test. According to the slide, it gives more credible results than Dixon's test in that range. For a sample size roughly between 10 and 40, we first calculate two things: the mean value, m, and an estimate of the standard deviation of the general population, written here as S sub n minus 1. So this is the point where the statistics become slightly more grown up, still manageable, but definitely wearing a tie. In the first version of Student's test, we calculate the distance between a potential outlier, called x0, and the mean value of the distribution. This is done using the t-statistic formula shown on the slide. Then we compare the obtained t-value with the critical value t-critical for the appropriate dataset size. If t is greater than t-critical, the outlier is considered real and should be removed from the dataset. So conceptually, this is very clean. We ask, how far is the suspicious point from the center relative to the spread of the data? If the answer is much too far, then the point is officially in trouble. The second version of Student's test expresses the same logic in a slightly different way. Instead of calculating a t-value for one suspect, we calculate the lower and upper trust limits of the distribution. Then we simply check whether the potential outlier falls inside or outside that range. If it lies outside the calculated trust range, then it is considered a real outlier and should be removed from the dataset. So this version is a bit like drawing a statistical fence around the acceptable data. If the suspicious point stands outside the fence, it does not belong. A little harsh, perhaps, but mathematically efficient. If the dataset is large enough, meaning more than 30 observations, we can use a simpler, more empirical version of Student's test, the 3 sigma rule. The idea is based on the fact that for large datasets, the t-distribution becomes very similar to the normal distribution. And in a normal distribution, most values sit reasonably close to the mean. According to the slide, about 2/3 of the values fall within 1 sigma, almost 95% within 2 sigmas, and about 98% within 3 sigmas. So the practical rule is simple. If a suspicious value lies farther than 3 sigmas from the mean, it is treated as a real outlier and should be removed. In other words, if a point lives that far from civilization, statistics begins to lose patience. Now we return to the example from the previous lecture. 20 samples from a retention reservoir, described by 5 variables. Earlier, 2 variables looked suspicious, TB and CLO. So now the goal is to decide whether the problematic objects are genuine outliers, meaning they may come from a different general population, or whether they only look suspicious. This is a very nice transition from theory to practice, because slides full of formulas are lovely, but sooner or later the data demand a verdict. Here we analyze the TB variable, the sample PW5 with TB equals 0.462, looked like a potential outlier. So PW5 was temporarily removed, and the histogram of the remaining data was checked. But the resulting distribution was still right skewed. That means the problem was not really the object itself. The problem was the shape of the variable. So PW5 was restored, and a transformation TB star equals log of TB was applied. And the final conclusion was that PW5 is neither an outlier nor a mistake. It was only an illusion created by the skewed distribution, a classic case of statistical slander. The sample looked guilty, but the histogram cleared its name. Now we look at CLO. Here, the suspicious object is RW1, with CLO equals 0.86. Again, RW1 was temporarily removed, and the remaining histogram was examined. This time, the resulting distribution was left skewed. Then RW1 was restored, and several transformations were apparently considered. But none of them managed to normalize the distribution properly. So unlike TB, this case remains suspicious. The conclusion here is cautious but clear. RW1 might be a real outlier, so we need to apply Student's test. So the plot has spoken, but not yet with full authority. Here the first version of student's test is applied to the CLO example. The mean value was calculated as m equals 2.92 and the estimated standard deviation as s equals 0.294. Then, the distance between the suspect value, 0.86, and the mean was converted into the t-statistic, which came out to 7.01. The critical value at alpha equals 0.05 and 18 degrees of freedom was 3.33. Since t is greater than t critical, the conclusion is straightforward. RW1 is a real outlier and should be removed from the dataset. So this time, the suspect did not survive cross-examination. And here, we verify the same conclusion using the second version of student's test, the one based on the trust range. Again, the same mean and standard deviation were used, and the lower and upper trust limits were calculated as approximately 1.98 and 3.86. The value 0.86 does not fall within that interval, so the conclusion is exactly the same. RW1 is an outlier and should be removed, and that is always comforting in science. 2 roots, 1 answer, less room for drama. Now we move to a very important topic, transformation of variables. Why do we transform a variable at all? According to the slide, there are 2 main reasons. First, to normalize the distribution of a variable. Second, to linearize a non-linear correlation. So transformations are not cosmetic tricks. They are not there to make the data look fancy. They are there to make the data more suitable for proper analysis. Basically, we are not cheating. We are negotiating with reality in a mathematically polite way. Sometimes during data control, we discover variables whose distributions deviate strongly from normality. And this matters because some chemometric techniques require each variable to be approximately normally distributed in order to work correctly. If we apply such methods to badly non-normalized variables, the results may be misleading or simply wrong. So normalization is not a decorative luxury, it is often a practical requirement. In other words, before asking the method to be clever, we should first give it data that are not actively trying to sabotage it. This slide gives the first practical recipe. If a variable starts at 0 and shows a strongly right-skewed distribution, then useful transformations include log x, or the 4th root of x. The general goal is to compress the long right tail and make the distribution more symmetric. So this is one of those moments where a simple mathematical function can dramatically improve the behavior of the data, which is honestly one of the more satisfying things in chemometrics. Here we get the second practical recipe. If the variable is strongly right-skewed and the mean/max ratio is below 0.1, then a suggested transformation is log x minus a, where a is smaller than x. So instead of applying a plain logarithm directly, we first shift the variable by a constant and then transform it. That gives us a little more flexibility when the simple version is not good enough, and this is where chemometrics becomes slightly artisanal. Not random, of course, but definitely requiring some judgment, some iteration, and occasionally a little statistical intuition with coffee. Here we get another practical normalization rule. If the distribution is strongly left-skewed, the suggested transformation is x prime equals log of a minus x with a greater than x. So this is basically the mirror image version of the earlier logarithmic transformation for right-skewed variables. Instead of compressing a long right tail, we now tame a long left tail. And once again, the goal is not mathematical decoration. The goal is to make the distribution more symmetric and more cooperative, because some variables are not evil, they just need a little persuasion. Now we move to a special case, percentage variables. If a variable is expressed as a percentage and its values are mostly below 15%, the suggested transformation is simply log of x. This makes sense, because percentages crowded near 0 often behave in a strongly asymmetric way. So this is a nice reminder that not all variables should be treated identically. The numerical form of the variable matters, and percentages have their own little statistical personality, which, as always, means more work for us. And here we get the opposite percentage case. If a variable is expressed as a percentage and the values are mostly above 85%, then the suggested transformation is log of 100 minus x. So instead of looking at the value itself, we transform the remaining distance to 100%. This is a clever trick because values crowded near the upper limit of a scale can be just as awkward as values crowded near zero. In other words, whether the data are squashed near the bottom or near the top, statistics still finds a way to make your afternoon interesting. Now we arrive at one of the more practical and slightly less elegant truths of chemometrics. The A value in these transformation formulas usually cannot be calculated directly. It has to be found empirically. According to the slide, usually 3 or 4 attempts are enough to find a suitable value, and the only real criterion is the shape of the resulting histogram. So yes, this is partly mathematical and partly experimental craftsmanship. Sometimes the honest answer is not, we derived it beautifully, but rather, we tried a few sensible values and the histogram finally stopped looking offended. Here we begin a practical example. A certain feature was measured for 17 objects, and the observed distribution is strongly left skewed. So the appropriate transformation should be x prime equals log of a minus x. And the key question becomes, what is the best value of A? This is a good moment to remember that transformation is not only about formulas, it is about choosing the right formula with the right parameter, and that second part is where patience earns its salary. Now the trial and error part begins. The maximum value of the variable is 4.859, so we know immediately that a must be greater than the maximum. The slide suggests trying a equals 4.9, then perhaps a equals 5.0, and then a equals 5.5. This is exactly the kind of empirical tuning we talked about on the previous slide. You start with values that make mathematical sense, and then you inspect what happens to the distribution. So yes, this is science, but it is science with a little bit of knob turning. And now we get the verdict. For a equals 5.5, the distribution becomes right skewed, which means this value is too high. So the correct value should lie somewhere between 5.0 and 5.5. The final trial shown on the slide is a equals 5.2, and the conclusion is nicely realistic. The result is not perfectly normal, but it is at least roughly symmetrical, which is the best achievable outcome here. And I actually like that slide for its honesty. Sometimes data do not become perfect, they just become better. And in real chemometrics, a better is often a very respectable victory. Now we move to the second big reason for transforming variables, linearization. Chemometrics loves linear models when describing dependencies between variables, but sometimes a correlation plot reveals a relationship that is clearly strong, yet clearly non-linear. In that situation, one or both variables should be transformed so that the relationship becomes linear. That process is called linearization. So the message is simple. If the relation is real but curved, we do not necessarily give up. We transform the variables and try to straighten the story a little. Very much like academic life, actually. Here is the first practical rule for linearization. If the correlation has a vertical asymptote at x equals 0, then suggested transformations include log of x or 1 over x. So this is the kind of relationship where the curve becomes very steep near 0 and then gradually relaxes. The transformation is chosen to stretch the compressed part of the relation and make the overall trend more linear. This is one of those moments where a plot may look hopelessly curved at first glance, but one smart transformation can suddenly make it behave like a civilized straight line. And here is the next case. If the correlation has a vertical asymptote at x equals a, with values x minus I greater than a, then suggested transformations are log of x minus a or 1 over x minus a. So this is a shifted version of the previous situation. The asymptote is no longer at 0, but at some other critical value, which means that before transforming the variable, we first need to respect where the curve is actually anchored, because in chemometrics, as in diplomacy, everything depends on context and proper positioning. Here we get the third asymptote case. If the correlation has a vertical asymptote at x equals a, but now the values satisfy x sub I less than a, then the suggested transformations are log of a minus x, or 1 over a minus x. So this is again a shifted asymptote, but on the other side of the boundary. And that matters because using the wrong sign here would be a very efficient way to create mathematical sadness. The main point is simple. Before transforming the data, we need to understand on which side of the asymptote the data actually live, because chemometrics is many things, but guessing the sign blindly should not be one of them. Now we switch from the x-axis to the y-axis. If the correlation has a horizontal asymptote at y equals b, and the observed values are below b, then the suggested transformation is y prime equals log of b minus y. So instead of transforming the predictor, we now transform the response. That is a useful reminder that nonlinearity does not always have to be fixed on the x side. Sometimes the real issue is how the y variable approaches its limiting value. And when that happens, the response variable politely asks for transformation therapy. Here we get the mirror version of the previous case. If the correlation has a horizontal asymptote at y equals a, and the values are above a, then the suggested transformation is y prime equals log of y minus a. So once again, the logic is based on distance from the asymptote. We are not transforming the raw value for fun, we are transforming how far the value still is from its limiting behavior. This is actually quite elegant. Slightly fussy, yes, but elegant. And now we arrive at the dramatic one, the sigmoidal curve. If the relation is sigmoidal and has two horizontal asymptotes with a less than y sub I less than b, then the suggested transformation is y prime equals log of y minus a divided by b minus y. This is a classic way to straighten an S-shaped dependence into something more manageable. So the lesson here is that even if the original relation looks quite fancy, curved, and biologically or chemically dramatic, there is often a transformation that brings it back into the comforting world of linear models, which is exactly where chemometrics likes to drink its coffee. Now we begin an example. An object's response, y, was measured for 17 different values of x. A correlation plot was prepared, and the relation is clearly visible, but just as clearly non-linear. The first proposed transformation is x prime equals log of x. So this is the moment where theory finally meets a real plot. And as usual, the plot looks at us and says, yes, there is definitely a pattern here. But no, I will not make your life easy. After applying the transformation x prime equals log of x, the result is better, but still far from truly linear. So the slide proposes a second attempt, x prime equals log of x minus a, with a somewhere around 0.1, and this is a very realistic chemometric moment. The first transformation improves the relation, but not enough. So we refine the model rather than pretending success too early, which is a very scientific habit, and also an excellent cure for overconfidence. Now the transformation becomes x prime equals log of x minus 0.1. The relation improves again, but the slide is refreshingly honest. It is better, yet not perfect. So we try to improve it further, now with a equals 0.15. This is exactly the same spirit we saw earlier while choosing the best of value for normalization. Sometimes you do not hit the best transformation immediately. You move toward it step by step, using the plot as your guide. So yes, this is still math, but it is math with feedback. And here we see the transformation x prime equals log of x minus 0.15. This appears to be the improved version that the previous slide was aiming for. At this point, the relationship looks much more linear than in the original plot, and that is the big practical takeaway. A good transformation does not need to be mystical or glamorous. It just needs to make the structure clearer and the model more appropriate, which honestly is already a pretty noble job for one logarithm. This slide continues the same transformed example, again with x prime equals log of x minus 0.15, reinforcing the final improved shape of the relationship. So by this point, the message is quite clear. The original nonlinear dependence can be substantially straightened by using a shifted logarithmic transformation, and I actually like that the lecture shows the process across several slides instead of jumping straight to the final answer, because that is how real work usually looks, not magic, iteration. And now we open the next chapter, exploratory analysis. According to the slide, multidimensional analysis of data structure is called exploratory analysis. It can be treated either as a part of dataset preparation for further analyses or as a chemometric technique in its own right. Its goals are to analyze relations between objects or samples using a multidimensional approach and to define relations between variables in multidimensional space. So this is where the course starts widening its lens. We are no longer looking only at one variable or one pair of variables. Now we begin asking what the whole data structure is trying to tell us. And that, as always, is where things get very interesting. Now we begin to classify the main approaches used in exploratory analysis. According to the slide, there are two major groups of methods. The first is analysis of similarities, which is based on distances between objects and variables in multidimensional space. The second is component analysis, which focuses on how the variability of the dataset is distributed across the original variables. So one family of methods asks, who is close to whom? And the other asks, where is the variability really coming from? Two different philosophies, both very chemometric, both very useful. At the beginning of exploratory analysis, we assume something very honest. We do not yet know the structure of the data. What we do have is an X matrix, where n objects are described by m variables. So this matrix is the starting point. The raw organized form of the dataset before deeper structure is uncovered. And I actually like this slide because it is conceptually important. Before PCA, clustering, or anything sophisticated happens, the data are just there, sitting quietly in a matrix, pretending to be innocent. Then, Chemometrics arrives and starts asking uncomfortable questions. This slide nicely reconnects the earlier parts of the lecture with exploratory analysis. After data acquisition, the variables should be controlled and transformed if necessary. And here the lecture reminds us of the three main reasons for transforming variables: to normalize a distribution, to linearize a nonlinear correlation, and to prepare the data for multidimensional analysis, especially through data centering and order scaling. So the previous slides were not just a statistical side quest, they were preparing the terrain for the real multidimensional adventure. Now we come to data centering, one of the most basic and most important transformations in chemometrics. Data centering is a linear transformation, basically a translation, that shifts every variable so that its mean value becomes the center of the coordinate system, usually 0. Importantly, this operation does not change the relations between objects in multidimensional space. What it does is simplify mathematical operations and make data presentation more convenient. Mathematically, each value is transformed by subtracting the mean of its variable. So every value of variable x sub m becomes x prime sub mn equals x sub mn minus x bar sub m. So centering does not rewrite the story, it just moves the whole story so that 0 sits in a more useful place. Here we begin a concrete example. Concentrations of Fe2+ and Cl- were measured for 5 water samples, and the original values are shown both in a table and on a plot. The mean values are approximately 0.49 for Fe2+ and 0.85 for chloride. At this stage, the data are still expressed in their original coordinate system. So this slide gives us the before picture, and as always, the before picture exists mainly so the after picture can look clever. Now we see the same data after centering. Each original value has been reduced by the mean of its variable, so both variables now have means equal to 0. The centered values are shown in the table, and the plot is now organized around the origin rather than around the original concentration levels. And this is the key point. The relative arrangement of the samples is still there. We did not destroy the structure. We only shifted the coordinate system to a more mathematically convenient position. So centering is not dramatic, but it is extremely useful. Now we meet another crucial issue: commensurability of variables. The result of chemometric analysis should not depend on the units in which the variables are expressed. For example, if one variable is expressed in thousands or millions and another in small decimal fractions, the large-scale variable may dominate calculations, such as Euclidean distance, simply because of its numerical magnitude. That is obviously not ideal. We want the analysis to reflect structure, not merely unit choice. So we apply an additional transformation called scaling. And yes, scaling is often associated with centering, because chemometrics enjoys teamwork. The goal of scaling is to ensure that all variables in multidimensional space are expressed at the same order of magnitude. The slide lists 2 main approaches. The first is rescaling, also called min-max normalization, which places values within a fixed range, typically from 0 to 1. The second is variance scaling, which ensures that all variables have equal variances. So this is really about fairness. We do not want one variable shouting while the others are forced to whisper. That may work in politics. It is less charming in chemometrics. Among variance scaling methods, the one most commonly used is standardization, also known as autoscaling. After autoscaling, all variables have the same variance, equal to 1, and each value is transformed using the familiar formula. Subtract the mean of the variable, then divide by its standard deviation. So, autoscaling combines data centering and variance scaling in one operation. That is why it is so popular. It is efficient and conceptually clean. In other words, autoscaling is the chemometric equivalent of saying, everybody line up, calm down, and stand on the same scale. Now we begin an example with 2 variables, x1 and x2. Their means and estimated standard deviations are given on the slide. For x1, the mean is 5.98 and the standard deviation is 2.98. For x2, the mean is 0.91 and the standard deviation is 0.43. The original scatter plot shows the raw relation between the 2 variables. And at this stage, because the scales are different, the structure may not yet be fully visible. So this is another before slide, which means the transformation is about to earn its paycheck. Here we see the same dataset after autoscaling. Now both variables have mean values equal to 0.00 and standard deviations equal to 1.00. And the slide adds a lovely observation. Inner data structure was revealed. That is exactly the practical benefit of autoscaling. Once variables are placed on comparable footing, genuine structure becomes easier to see. So sometimes the data were interesting all along. They just needed a fair coordinate system to confess. This slide shows another benefit of autoscaling. It can also help in searching for outliers. According to the slide, after autoscaling, the distribution of the x2 variable exhibits high asymmetry, and that asymmetry is caused by an outlier. So autoscaling is not only about preparing the data for later multivariate analysis. It can also sharpen our perception of suspicious structure, a bit like cleaning your glasses and suddenly noticing that one data point has been acting weird all day. And here we reach the final slide of this lecture. After all the transformations, the result is a Z matrix, which can then be subjected to further exploratory analysis or other chemometric techniques. So that is the overall logic of the lecture. We started with raw data, checked for outliers, transformed variables when necessary, centered and scaled the data, and ended with a processed matrix ready for deeper analysis. In other words, the data are now no longer raw. They are civilized, and that is a very respectable place to end today's story.